All right. Welcome, everybody. This is Kathy Rezabeck, the ARCIS person. And this is the fifth and final webinar in our series. I think we may have a few more people to join in, but we'll just begin. I have no feedback. Everyone seems to be connected just fine. And we're going to, of course, record this series. It will be available to anyone who misses or who would like to see it again. Whoops. Once again, you know how to deal with questions. Please type your questions into the chat box as the presentation is going on, and I will try to take an opportunity to get those questions answered by our presenter, Mark Clark, today. Other than that, we'll have time at the end of our presentation for questions as well. Today the topic is, why is soil important? And our speaker today is Mark Clark. Mark earned his bachelor's degree in agricultural science with a soils option from Montana State University in 1979. He holds a master's degree in soil science with a focus on wetland soils hydrology. He has worked as a soil scientist for U.S.D.A., U.S. Department of Agriculture, Natural Resources Conservation Service in Montana, Arizona, and for the last 30 years in Alaska. He retired in 2013 and continues to work as an adjunct faculty for the University of Alaska Fairbanks. And he's coming to you today from Chickaloon, just north and east of Anchorage. Sam is struggling to get on Blackboard to see and hear. I'm afraid that we do not have a helper. Good. Sam is here. I'm glad to see that. Before I turn it over to Mark, I just want to let you all know that since this is the last in the series of our 5 webinars, after the session is over, I'm going to be sending each of you a very short evaluation. If you wouldn't mind filling that out, it will only take you about 10 minutes. We're always trying to figure out ways to make these sessions better. And should we hold another one next year, we would like to improve upon this year's. So if I'd appreciate it if you would do that. You'll get that from me, and it will be returned to Meg Burgett. All of that will be in the email. Speaking of Meg, who is the instructor of record for our credit course, those of you who are taking for credit, Meg will be sending you an email sometime in the next couple of days to give you the detail about our final meeting for the credit, which will be May 13th. So with that, what I would like to do is, the last several times we have tried to give our presenter a little bit more information about each of you. And in this case, if you would all think for a minute, your answer to the question, why do you think soil is important? And just go ahead and type that into the chat box. Why do you think soil is important? Don't be shy. All right. I see Meg Burgett has joined us. Well, while the rest of you who haven't responded think about it, let's take a look at the answers to some of the question. Meg thinks because it all starts with the soil. That's Meg Burgett. Helen, for a great garden. Russ Hall, so much of what we need to live comes from or is filtered through soil. Threat, because we are losing it. Shannon, because soil has the minerals and nutrients which are essential to all life. K, soil is the foundation for life, structure, and development of natural resources. And I see Emily and Sam have answered because it grows my tomatoes. Sam grows tomatoes. And it looks like Lyle is now joining us. We haven't quite started, Lyle, so you haven't missed anything. If you'd like to type in why you think soil is important, that would be great. And while Lyle is doing that, I just want to say that there are a few folks online who have a perfect attendance. And those folks are Helen, Lyle, Zach, Shannon. Those are the folks I show who have attended every single one of the webinars. And thank you. Well, I think what we'll do, because we have a very full presentation today, is I've introduced our speaker, Mark Clark. He is standing by. And I'd like to go ahead and turn it over to Mark. Thanks, everyone, and welcome, Mark.
Hi, thanks, Kathy, and thanks to the participants for your interest in soil science. Before I start today, I want to kind of make an announcement and for your information, the United Nations, the Food and Ag Organization, has designated 2015 as the International Year of Soils, and there'll be various websites throughout the year that will be providing a kind of a barrage of soils information from around the world that will be, I think, very informative and really focused on our future and our food when it comes to soil. So if you get a chance to just do a web search, and there's a number of YouTube presentations out there that are really informative, and I encourage you to just do a search on International Year of Soil, and you'll find an abundance of. Get you next slide, please.
Yes, and Mark, a few people have said that you're a little soft, so if you might get closer to your mic, that would be great.
Okay, let's try this. All right. Okay, so the topics from today that we're going to talk about in regards to soil is first we're going to start off with a little narrative on soil science as a career, and then proceed on to answer the questions. I mean, you folks have pretty much done my job for me. You've answered very well on why is soil important. But we'll look at soil science, the basics of the science itself, the properties, the processes, look at the soil profile, and then probably the important part of it is to look at soil-related issues and how understanding the soil makes us better land stewards. And then finally, I've provided some references for students and teachers. We'll spend a little time with that. Next.
Mark, I'm going to break one more time. People are still saying they can't hear you very well. I guess let's pause for a second, and I'd like a little bit more feedback. It's possible we may take you off your telephone and put you on your computer.
Okay, let's see. Does that help?
Hey, folks, could I get a little feedback? No, Meg says no. Can you turn up your mic at all on your phone, Mark?
Yeah, I think I have it all the way up.
All right.
Oh, yes, it's all the way up right now. Maybe I can see if that helps.
It's funny because I can hear you just fine, Mark, but apparently other folks can't.
Yeah. Okay. The phone microphone is turned up all the way. Let me see if I can. Let me try one other item here. I think that's, yeah, I think it's up all the way now.
Okay, let's just get a little bit more feedback from folks. Mark, would you talk just a moment more?
Yeah. Yes, let's see if that helped at all. I can see if I can adjust it here on the screen. Does that help at all?
Okay, now we have folks saying we can hear you just fine. I guess I'd ask Meg and Kay. You seem to not be hearing well.
Okay. Yeah, I tried it. I turned the audio adjustment up on the screen here, and that seemed to help some. The bar seems to be going up quite a bit further.
Okay, Meg says she cannot hear, so let us try something. I would like you to hang up, Mark, and take your computer off mute and use your computer.
Okay, we'll try that.
And Mark, you'll have to press that talk button in order to talk.
Okay. See if that is that better.
All right, folks.
All
is
right.
that better? All right. Now,
Okay.
good. Terrific. Take it away.
Okay.
Mark.
Let's go ahead and go to the next slide. Okay, so let's look at soil science as a career. So what is soil science? Well, soil science is a study of soils on the earth, and it includes the formation, classification, and mapping of soils, and it incorporates a number of disciplines and a number of aspects of our physical and chemical world, and as well as the biological components. So it is a very applied science, and we use soil scientists. Soil science is used extensively in the management of our landscape. So it encompasses biology, ecology, geology, and geography. And like I said before, it's a multidisciplinary, and it incorporates a lot of the technology as it develops for investigating soils remotely using GIS approaches, geographic information systems, other tools like ground penetrating radar, synthetic aperture radar, other tools that exist out there that help us remotely look at soils and monitor them on the landscape. Soil science integrates the concerns for people, food production, and the environment. So it's centered around all the activities of both the man-influenced and the natural world. Next slide, please. So what roles do the soil scientists play in our society? They bring the science and technology to issues involving soil and water resources. And this, I think this is paramount here. It applies the science to make wise soil and water resource decisions. It plays a key role in public and private decisions relating to these resources. And soil scientists are employed in both the public and private sectors for local, state, and federal agencies and universities, and both internationally and domestically. There's a big demand internationally for soil scientists with our stresses on our food resources across the world. Next slide, please. So what qualities are necessary? For soil scientists, and the reason why I went into soil science is I have a passion for science and I really enjoy working outdoors. Some of the other aspects of the science I acquired later on, but that was the driving force that pushed me into the science. But many folks, after they start to become involved, they develop a desire to be an integral in the environmental decisions that are related to soil conservation, land use, water quality, and waste management. And these folks, as scientists, tend to be fairly introverted. We need to have a willingness to communicate our knowledge about the science to really affect the decisions made in our society. Next slide, please. So how do I become a soil scientist? Well, you got to go to university. For the government service 470 grade soil scientist series in the federal government, you have to have a minimum of 15 credit hours and a bachelor's degree, and a degree consisting of strong fundamental science, soil chemistry, physics, fertility, and soil classification classes are essential, as well as being able to communicate these technical skills through writing and oral communication. Next slide, please. So what specific tasks would you do as a soil scientist? Well, they're really varied. There is a plethora of options out there, from research in the public and private research institutions to actually managing soils for crop production and forest productivity, teaching in college and universities, recommending soil management programs to state and federal governments, working specifically on watershed and wildlife management teams. This is really big. And then, of course, evaluating nutrient water availability to crops regionally as well as in individual fields. And then we can get down to the environmental science end of things, mine reclamation and site restoration, and also assessing environmental hazards, everything from like the landslides we saw in Washington State to other water quality, soils related issues. And also you can be involved in the regulation end of things, developing regulations for different activities that impact soils. Next slide, please. So we asked the question, why is soil important? This is the principal subject today. That the takeaway is that we need to understand a little bit better why the soil is so important in our lives. Next slide. Well, as was stated by some of the comments, it's an essential part of human life on Earth. We grow our food on it, we build our roads, houses, and businesses on it. Our water's filtered through it. And also soils are the foundation of wildlife habitat. Wild systems depend so much on soils. And there are a number of societies that have failed from a lack of care given to the soil resource. Next slide. A couple of examples I'd like to state. We can go way back into what's called the Fertile Crescent in the Mesopotamia area. This is the Tigris and Euphrates River in northern Iraq, the area of big concern today with ISIS. This area had the first documented irrigation system on Earth. And at around 2300 BC, there was these extensive irrigation canals that were built in this region. And through the years, they started adding saline water to the crops there, and the soils became more salty, and they had to shift to barley, which is less sensitive to salt. And then they eventually became so saline, the soils did, that they had to be abandoned. So this extensive area lost its productivity from their irrigation water management. Next slide, please. And we can come a little closer to home. The Mayans and the Yucatan Peninsula, they occupied that area from about 2600 BC to 1200 AD. Here there was extensive soil erosion and that was associated with overpopulation, overuse of the soils, deforestation, and this was all compounded by drought. So between 600 and 800 AD, many of the cities of the Yucatan and Central America were abandoned. The Mayan cultures, Copan, Tikal, and some of the other ruins that we visit today were abandoned at this time. Next slide, please. Another, the Rapa Nui, or Easter Island in the South Pacific Island, South Pacific Island, about 1700 AD. Here there was extensive soil erosion and fertility loss associated with deforestation. The area lost it was a very marginal climate to begin with, very, very severe, and they mined the fertility of the soil, removed the trees, and as a result, productivity declined. And the culture of the Moai, they're the ones that built the stela that you see here, they disappeared from the island at about 1700 AD. Next slide, please. And very close to home, of course, the Dust Bowl in 1920 to 1940. And this was a period when there was devastating erosion associated with the expansion of cultivation across the Great Plains. And this was in response to the depression and the drop in revenues. People were having a hard time making a living, so they started to expand into marginal soils and exercise poor conservation practices. This, combined with drought, ended up with devastation in the area. This is when my agency, which was then the Soil Conservation Service, was basically born under the Soil Erosion Service. Next slide, please. So, some important soil facts that I think are worth mentioning here. You know, there are more microorganisms in a handful of soil than there are people on Earth. That's pretty amazing. Microbes are just abundant in the soil. Soils reduce flooding by storing a tremendous amount of water per acre, and this buffers runoff and reduces flooding hazards. The soil, of course, acts as a filter for underground water, filtering out pollutants, and we'll talk about this a little bit later. And another fact, about 10% of the world's carbon dioxide emissions are stored in the soil. And to bring it even closer to home, permafrost soils in the subarctic and Arctic, even though they occupy only about 17% of the terrestrial planet, store about 35% of the Earth's land-based soil carbon. Pretty amazing. And another fact, we're losing approximately an acre of farmland per minute to urban conversion in the U.S. So about 91% of our fruit and over a quarter of our vegetables is produced in urban-influenced areas. Next slide, please.
Mark Lyle has made a comment about a book. He's wondering if you know about it, by Jared Diamond, called Collapse.
Yes, you know, there's Jared Diamond's book is very good. There's another book out there that I think is essential reading for anyone in the resources, and it's put out by the Earth Policy Institute. The author is Lester Brown, and it's called Plan B 4.0. And I didn't include it in the references, but it's a really good book. He worked for this Lester Brown worked for the State Department for years, and the book is focused on the impacts on our natural resources worldwide and some of the solutions to face those. And that book, you can get it online for free just by going to Plan B 4.0, and it's a PDF book. And there's some of Diamond's work that's cited in there, but this is a little more comprehensive too in terms of resources. It's a very good book, and I'd suggest reading it as well as Diamond's.
I see that
Okay.
another book has been
Next slide,
suggested by
please.
Shannon, Guns, Dirt, and Steel.
Yes, and that's another Diamond book as well, and that's another one that he wrote, and in regards to kind of a cultural development in the world and its effect on society. And another good book. I think that's another Diamond book as well. Great. Hey, let's look at the science a little bit here. Next slide. First, let's start with the definition of soil. Operating definition is naturally occurring unconsolidated material at the surface of the earth that supports plants. And what we often don't know about soil is about half of soil, the volume of soil, is empty space, either occupied by air or water. And in mineral soil, roughly 45% of the soil is actual particles, and then the remaining part is organic material, roots, humus, organisms. So this is kind of our operational definition of soil, and these are the major components, the constituents that make up the soil here. Next slide, please. And so we need to understand that soils differ in terms of their physical and chemical properties. And I showed 3 soils here, one from Arizona, the desert, another one from south central Alaska, a humid temperate soil, and then a tropical soil from Hawaii. And there's obviously differences in these soils, physically, obviously from color, but you can well imagine that the chemical components of these soils are also different. We'll talk about physical and chemical properties a bit more here. Next slide, please. So the soil properties, we have physical and chemical properties, and the physical are related to the properties or actions of matter or energy, and these are primarily properties we can see, feel, we can measure by very simple tests, and they include the color. The properties include color, structure, texture, rock fragments, and permeability. And permeability is kind of the rate that water moves or contaminants move through the soil. Rock fragments, the amount of rock in the soil. Textures, the sand, silt, and clay components. Structure, the aggregates of soil particles, and color, the color of the soil itself. So anyway, and then the chemical properties, these are relating to the property and action of chemicals. And the primary ones we have are pH, the nutrients, and these are the macronutrients, nitrogen, phosphorus, and potassium. And then there's also metals. These are iron, aluminum, lead are examples. And then the one that I didn't list in here is cation exchange capacity. And this chemical property is the ability of the soils to retain and transfer nutrients from soils to plants. And it's a fairly complex activity that's associated with clay and organic material, cation exchange capacity. I have to apologize, I didn't list that one as chemical. Next slide, please. So physical properties. I asked, well, I was given a class one time to high school kids, and one of the children in the class asked me, said, Mark, what is the most important properties, or what is the most important property of soil? And I said, well, I'll reserve two properties, and we'll talk about one here, and that's soil texture. Soil texture is probably one of the most important properties of soil. If I know the soil texture, I understand a lot about the soil. And the soil texture, by this we mean the primary size fractions, the sand, silt, and clay. And we all know what a sand particle looks like. If we blow that up to the size of this background sand unit I show here on the screen, it gives you a relative comparison of sand, silt, and clay. Clay is less than 2 microns in size. You can't see it. You only see it with a microscope. Silt, you can see it with a hand lens, but you have a difficult time seeing it with your naked eye. And of course, sand is visible to the naked eye. And the importance of texture, because it influences how fast water moves through the soil. Of course, the sandy soil, it moves through faster. Clayey soil, it moves very slow through it. And it affects how much water is held for plant use. Sandy soils obviously hold a lot less water, and they become droughty very quickly, or they don't support plant growth very long before you need additions of water. And clayey soils have a higher available water capacities and retain their water much better. And also the quantity of nutrients retained is based on the textures. The clay soils retain many of their nutrients, whereas the sandy soils do not. They don't have that sand, or the sandy soils don't have the clay or the humus to hold on to the nutrients that may fall in the soil, so it passes through quite rapidly. And of course, susceptibility to frost heave and swelling. Sandy soils are not susceptible to frost heave and swelling, and clay soils very much susceptible to frost heave and to swelling and shrinking from variable water contents. Next slide, please. And most soils are a mixture of these fractions, sand, silt, and clay, as shown in this U.S.D.A. textural triangle, with clay in the upper point, sand in the lower left, silt in the lower right, and the percentages, relative percentages of these are illustrated in the middle with these modifiers or descriptors for the mixtures of various amounts of sand, silt, and clay. As you notice, most soils within this triangle are some sort of a loam, clay loam, sandy clay loam, and this is the textural triangle that is a very commonly used. It is the basis for the U.S.D.A. soil textural classification. Next slide, please. And physical properties. So let's look at why is soil color so important. And that's the big question. And soil color is really important because a lot of the chemistry and the mineralogy of the soil is related to the color of the soil. In the left photograph here, our desert soil, we notice it's fairly bright in color. The only thing that we see is kind of this white zone at the tip of the arrow, which is primarily salts, calcium carbonate, and sodium chloride, and it imparts a white color to the soil. So this is one of the pigments. Salts are soluble salts, and calcium carbonates are pigments of the soil. In the middle photograph, we have this dark surface area, and you also see a light area in there. Well, the light areas where there is very little organic material, and the dark areas where there's high amounts of organic matter. So organic matter makes the soil dark. And in the tropical soil from Hawaii, we have a high amount of weathering in the soil. So there's a lot of iron oxides and aluminum oxides. And so it imparts a very red color to the soil. So iron is one of the principal pigments of soils. Next slide, please. And how do we document soil color? We use what's called a Munsell color chart, and it's organized by page based on hue, and hue is primarily wavelength. Red with, and they're arranged from red in the front of the book to yellow in the back of the book. Again, wavelength related. And then on the on the vertical axis, we have a value. It's arranged by value, and value is either the lightness or the brightness of the soil. And then on the bottom, on the horizontal axis, we describe the soil also based on chroma, and this is the purity or intensity of the color on the chip. And I know this stuff is fairly abstract, but Munsell is used for paints. All the paints, when you go to the store and order paints for painting your house or a room in the house, and this Munsell hue, value, chroma arrangement is used to describe those colors and catalog them. Next page, please. Next slide. So physical properties. The next thing we're going to talk about is soil structure. And soil structure is very important in the soil because it influences water movement and is a real good indicator of soil health. And so when we start talking about soil structure, we start talking about the structural units of soil. The particles are held together in these structural units we call heads. And so soil structure, it forms through a variety of processes, through shrink swell. Soils with higher clay content normally have better defined structure. It forms through frost action. Ice lenses forming in the soil can produce kind of a platy type structure. And then soil fauna and animals promote soil structure by burrowing through it and through their secretions. They cause the soils to form these aggregates. And plant roots are real effective in breaking up the soil and adding organic compounds. And these compounds cause the soil to stick together much better and form good structure. So what does soil structure do to other soil properties? Of course, it lowers the density of the soil, which means it adds airspace to it, increases the water holding ability, and the tillability. It's easier to till or tilth. It also indicates that there's a higher amount of organic material in the soil, and this higher amount of organic material means that a lot of the nutrients are held more tenaciously by the soil and are available for plant growth. And again, this is a physical property that can be significantly impacted by management. Next slide, please. So here's some soil structure examples. The one in the upper left is a granular. It's like little BBs. The soil is aggregated into these small BBs that are fairly uniform in the soil. The right one, the blocky one, is a coarser aggregate that is, that's where they form these actual little blocks in the soil, more of a lower organic matter and fewer roots. You tend to have these larger structural units that form. In the lower left, the platy one is formed oftentimes by freezing and thawing in the soil. It forms these little platelets. And then in soils that show no structure, we call it massive. It's massively or structureless soil material. And then sandy soils that don't stick together, we call it single grain. Next slide, please. So here's an example of what we call columnar structure. You can see this is a fairly high clay soil, and you can imagine that the structure really assists in water movement downward in the soil profile, and organic material or anything else that might fall into the cracks. Next slide, please. And here's a comparison of the same soil, with poor structure and good structure. Quite a bit of difference. You notice the higher organic matter content on the right side and the very well-developed granular structure in the soil. Water moves better through it. Roots penetrate it much easier, much better conditioned. Next slide, please. So what affects this structure? Well, tillage. The more we till it, the less structure we have. So in recent years, we've gone to more minimum till, what we call minimum tillage on landscapes here to try to maintain the structure. The old technique down below, moldboard plowing, used to turn the soil over, and they do it every time they plant something. Degrades the structure, as you can see in the right photograph, creating this what's called a plow pan, this flat area near the surface where water and roots have a hard time penetrating. Next slide, please. So chemical properties. Let's look at a few of these. Next slide. Okay, so chemical properties. This is the other part of that equation that the high school kid asked me about important properties. The two properties that if I know these properties, I know a lot about the soil. I know them probably a significant amount about the soil. Texture and soil pH. So soil pH is used in science and in medicine. It's a highly important measurement. And by definition, it's the negative log of the hydrogen ion concentration. That ought to scare you away. And basically, this means that the higher percentage of hydrogen, the lower the pH will be in the soil. And the less hydrogen in the soil, the more alkaline that soil will be. So we basically say that in soils 1 to 6 are acid soils. They have high hydrogen content within the soil on the soil exchange sites. And soils from 6 to 8, they're neutral. They have kind of a balance of nutrients and hydrogen. And then at 8 to 14, they're dominated by soluble salts and other alkaline elements in the soil, so the pHs are 8 to 14. Next slide, please. So pH is really important in terms of human health. I mean, our bodies survive within 1 pH unit. Below 6.8, we die from acidosis, acid conditions in our soil. That's a very, very common affliction. And then above 7.8, we die of what's called alkalosis, too many alkaloid minerals in our blood system. So life is possible in a very, very low threshold range of pH. Next slide, please. So in the soil, nutrient availability and toxicity is defined by the pH. And if we look at this upper pH range here, you notice that between 5.5 and 7.5, all of our macronutrients, the nitrogen, potassium, and phosphorus, is highly available in the soil. So that is why we strive for those neutral pH levels. At low pH levels, aluminum, iron, manganese, zinc, a lot of these metals become toxic in the soil. They become overabundant and they start to impact plant growth. At pHs above 7.5, calcium, and we don't have it listed on here, but sodium and other soluble salts begin to impact and make plant growth very difficult. Next slide, please. Okay, so managing the soil pH. Well, we add a very basic component to the soil if we want to raise the pH. We add lime, which is either calcium or magnesium carbonate, and this helps us raise the pH. We have to add a lot of it. And then in the other direction, if we're too basic and we need to drop it, then we add acid components like sulfur-based compounds, ammonium nitrate to lower the pH. This helps us strive for that that approach neutral as much as possible, or in that range. Okay, next slide, please. So we're going to talk a bit about soil formation and processes. Next slide. Okay, so in terms of soil formation and soil processes, I'm going to refer to a Swiss soil scientist by the name of Hans Jenny. And he proposed that by understanding 5 variables, environmental variables, terms, and he called these state factors, one could predict the type of soil that forms at any point on the landscape. And we'll talk about these soil forming factors a bit more. Next slide, please. And he said that if we understand the climate, the amount of rainfall, temperature, evapotranspiration, if we understand the biota, the plants and the animals that occupy that landscape, both the microbial populations and the invertebrates, as well as the vertebrates on the site, if we understand the relief, the steepness of the slope, the shape of the slope, and the aspect, we can understand the types of soils that start to form. And when I say relief, steepness or shape means if it's concave, it's going to collect water. If it's convex, water is going to run off. So it'll be, shape really affects the water, the state of water on that landscape as well. And then very steep soils, of course, are very much more erosive, so that affects soil development. Parent materials is the next factor, and this means the source of the materials in which the soil is formed in, and we can talk about glacial materials, floodplain materials, windblown, as well as the different types of bedrock, because they have different chemistry, igneous, sedimentary, and metamorphic. And finally, the final factor, time. How long has the surface been stable and not receiving new deposits of material? So this means that the climate can act on on those other factors over a period of time. You're going to have a different soil than if the soil was very young. So the soil equation is a function of these 5 soil forming factors. Next slide, please. So let's talk a little bit more about one of these variables, parent material. Definition: this is the kind of earthy materials in which the soil forms, and the process that's responsible for its origin. And next slide, please. I think this will become a little bit more apparent. Here's a dominant parent material in Alaska. We call it aeolian material. This is airborne deposits. The source is from loess. We know we've seen wind blow off the Knik and Matanuska rivers. We've seen sand. The middle photograph here is the Kobuk sand dunes. This is wind-deposited sand. And then on the right is we're looking at volcano. This is Augustine volcano in the inlet. So volcanic ash is a parent material that's an aeolian or airborne deposit. Next slide, please. So alluvium, this is water deposited materials. This is associated with floodplains, and these materials are often stratified, as you see in the image here, with multiple flood episodes. It buries organic material. You get this very stratified looking profile here, and this is a very typical alluvial deposit. Next slide, please. Ooh, I got bumped out here.
Okay, I think what Mark's talking about is he may not be able to see his slide. And
yeah, I'll
hold for. Let's give him a moment to get back in. mentioned to me earlier that they were doing some work on cables in his area, and he didn't have real great internet earlier today. Mark, are you there?
Yes, I'm trying to reconnect.
Would you like to bring up your PDF and continue that way?
You know, this is actually, I think it's going to kick me back in here.
Okay. We'll hold for a moment here.
Okay. Yeah, it's relaunching the Blackboard here. For some reason it bumped me out of it, and it's coming back up right now. It should only take a minute, and
okay, Kay has posted a challenge on chat. Take a look at it. Any ideas?
Okay. Okay, I'm back.
Our phone?
Yeah. Not sure.
Okay, hang up your phone and go back to the computer audio, please.
Okay. Oh, okay.
Mark, have you hung up your phone?
Yes, I have.
Okay, this is not going to work for us. We're getting a whole bunch of feedback. I think it might be better if you pull up the PDF. You could try again here to say something, and we'll just make a decision.
Okay.
Go ahead and say something.
Yeah, I don't know why I'm getting feedback. Maybe I just need to. I'm just.
Usually that happens when there is the phone on and the computer audio on. If you have only the computer audio on, something else is going on.
Yeah. How about now? How about now?
Now you sound good.
It sounds like I'm feeding back, but
Mark, you are feeding back. I think it might be best at this point for you to pull up the PDF and just call back on your hard-wired telephone.
Okay.
Mark and I actually talked about this scenario because of the work that was done on the cables in his area this morning. So I guess it has come to be. So he's going to pull up the PDF. He actually could pull up his PowerPoint, and we'll just continue. He'll call in, which means that we may not hear him quite as well.
Mark Clark.
Hi, Mark. We can hear you.
Yes, I'm back in.
Okay. And it just occurred to me that you could pull up either the PDF or your PowerPoint there on your computer and stay with us.
Yes.
Yes, I'm still getting feedback now.
Yes, you are.
Let me look at the system preferences and see if there's something going on here.
All right.
Okay, is that better? No, gosh. For some reason I can't get the input levels off.
This is on your telephone?
This is actually on the screen.
Okay.
So I will go ahead and bring up the PowerPoint and get off here.
And then you will call in on your telephone, I assume.
Yep. Yeah.
Okay.
Okay. So. Well, it's not going to matter because for some reason I can't squelch or mute the microphone here.
You can't.
In the system preferences, it won't mute my microphone.
On your computer.
Right. So is that work? No, it's still feeding back.
Mark,
Oh, here we go. Let's see if this does it. I mean, it shouldn't, but it's feeding back at your end.
Okay.
Okay. Yeah, it's still feeding back.
It sounds like Meg and Kay do not hear the feedback. Maybe it's just you, Mark.
Yeah, I'm just I'm trying to figure out how that's happening because I'm completely out of the Blackboard.
So it must be on your phone.
Okay, let's.
Looks like Lyle does hear it.
Okay, let's try this. Is that better?
Go ahead and say a few words.
Okay, yeah, I think we're fine.
I think we've got it. Thank you. What did you do there, Mark?
Well, it looked like there were two instances of the Blackboard that were open, and and the other one was in hiding. So.
Okay.
so we've got it.
Okay, great. Thanks.
Something. So I will go ahead and proceed with my the PDF I have here. And,
okay, Mark, and people are again asking you to speak up if you can.
Okay. Okay. So the next slide, parent material, is the slide is parent material colluvium. And I just want to make sure you have that one up on your screen so we can proceed.
Yes, that's what we have. Parent material, colluvium mixed and moved by gravel.
Yes. Okay, we'll go from there. Okay, so this is the material that's mixed and moved by gravity on steeper slopes. So colluvium is a specific parent material. Next slide, please. The next parent material is glacial drift. And this is deposited by glacial activity, being physically bulldozed or water that is being emitted from the glacier itself. And most of south central Alaska and southeast Alaska this is a very dominant parent material within those regions. Next slide, please. The next material is called cryoturbate, and this is material that's modified and moved by frost. And this is common in the permafrost areas of Alaska. So it's oftentimes modified by frost heave and moved by gravity as well. And cryoturbate is the term that we use. Next slide, please. The next parent material is residuum. And this is material that's unaffected by transport or the other processes that we talked about previously. This is material that's stable, and it's broken down by physical and chemical properties in place without alteration by other processes. Next slide, please. So we come back to our three soil profiles, and we find that there is difference in the soil forming factors that we talked about previously that produce differences in the soil. And it's a little bit easier to conceptualize why we have these different soils as influenced by these different 5 soil forming factors. We'll talk about this just a little bit more. Next slide, please. So, soil processes are the drivers in the soil soil formation, and these primary soil processes can be broken down into additions, which would be like dust, flooding, rain, or salts that land on the surface or are moved through the soil. Losses, this would be erosion, gases like CO2 as organic material decomposes, and materials are leached through the soil and lost from the soil profile. The next one, transformations, would be weathering in place, like oxidation of soil materials, which is associated with reddening, or reduction of those materials, which could be graying or associated with the reduction of iron in the soil. And then the final driver, translocations. This is movement of soil minerals, nutrients, and salts from one point in the profile downward, upward to a different location in the profile. Next slide, please. So we have our 3 soils back up on the slide here, and the desert soil, accumulations of salt and dust on the surface, typical process. Number 2, the losses from water and wind erosion from the surface, and translocations, those salts that occur within the soil profile itself, have been moved downward or in the soil as moisture percolates down through, or it moves upward in the soil as a dry surface pulls moisture to the surface. The tropical soil in Hawaii, we have an accumulation of organic material at the surface, which gives it this darker surface color. And further down, and the whole profile for that matter, represents transformation of clay minerals into iron and aluminum oxides. This imparts the very red color in these soils. This is a transformation of minerals from within the entire soil profile. And then the right profile, we see an accumulation of organic material at the surface. We see that dark surface layer. We see the gray area, which is an area where materials, organic materials, iron and aluminum, have been translocated through leaching, have been removed, giving it the gray leached color in this horizon. And then down below, these leached materials accumulate in the darker layers, and the reddened layers were represented by number 3. So it gives you some examples of these processes in the soil. Next slide, please.
If I could break in, if you cannot hear Mark, call the conference line, and I've placed it there in the chat.
Okay, does it seem to be a little weak yet?
Go ahead, Mark.
Okay, so we want to look at the actual soil horizons and associated processes. So typically in soil science, we break the soil horizons into these 7 categories. And the first is the O horizon, which is primarily loose.
Mark, we're having a hard time hearing you.
Okay. Let me see. Okay, so the A horizon is mineral matter that's mixed with soil humus or decomposed organic material. And this is a dark layer that we see in the upper part of the soil profile. And then the next horizon down is the E horizon. And this is a zone of where material has been leached, removed from this horizon, a transformation and a loss. And it's represented by a very light-colored horizon that's been leached of all mineral and organic materials. And this material accumulates in the next horizon, what we call the B horizon, which is often red or fairly reddish yellow in color. And this is a zone of accumulation of clay, iron, and aluminum. And it often originates from above but can form in place. And progressing down the C horizon is this partially altered parent material. It's been influenced primarily by physical properties and with few chemical alterations. And then below this, the R horizon, is where we have unweathered parent material. Next slide, please. Okay, so another example of an O horizon on the very surface, this E horizon, which is the leached horizon that's very gray, and nutrients and pigments have been removed through leaching, and they've accumulated down below in this darker and progressively yellower horizon with depth. And then at the very bottom, the unaltered parent material, or C material, is represented by this gray layer at the very bottom. Next slide, please. So we'll quickly look at the soil classification systems. And when we talk about soil classification, we talk about different classification systems for different applications. Next slide, please. So soils are grouped into classes for specific applications. The first one here, engineering. And this classification system, the unified, is used by engineers for building structures on the soil. There's another classification system called the American Association of State Highway and Traffic Officials. And this is called AASHTO, and this is primarily for road building suitabilities of soils. And then the next classification is the U.S.D.A. textural triangle. We looked at this earlier in the presentation. And then finally, there's a scientific classification of soils we call soil taxonomy. And this is the scientific classification which is used for the transfer of science, so we can talk between scientists. And then there's another one, the Food and Agricultural Organization of the UN, that uses a classification similar to our soil taxonomy for science purposes. Next slide, please. And I'm just going to show an example of the soil classification system, soil taxonomy. There are 12 soil orders that are included in soil taxonomy. And of the 12, 7 of them are the ones in red are represented in Alaska. And we won't go into detail on these, but each one of those has a specific arrangement of horizons and processes that are recognized at the highest level in the classification system. So you can look at the 12 orders a little bit closer in these descriptions and get a better idea for what they represent. Next slide, please. So the last part of this presentation is a quick look at the land use issues associated with soil science. Next slide, please. And the first issue we're going to look at is water pollution. And this is a very important issue because there's over 42,000 impaired water bodies in the United States, or 40% of the water bodies. And pollution can be described as either point pollution or non-point pollution. And point pollution is a discrete conveyance of pollution from an individual point on the landscape, like a pipe or a ditch from an industrial plant. And the more common and difficult pollution to try to handle or deal with is a non-point pollution. And this includes runoff, atmospheric deposition, drainage, seepage from tanks, or fertilizer losses such as nitrates. Soils have a very unique function in terms of remediation of pollutants, including these petrochemicals, fertilizers, heavy metals, and salts. So basically what happens is that these materials are retained within the organic and clay fraction near the surface of the soil, where microbial activity can degrade and detoxify, preventing these chemicals from entering into the water table. And the soil acts to both filter, detoxify, buffer, and degrade and immobilize these products and prevent them from hitting the water table. And in addition, wetlands serve a specific function. They reduce nitrates from fertilizer applications through an anaerobic process called denitrification, and it prevents these wetland fringes on rivers and lakes, helps to remediate nitrates and prevent pollution of water bodies through this denitrification process. Next slide, please. So the other soil issue is what we call impermeable surfaces. These are areas of the soil that are converted to impermeable surfaces primarily through urban development. And by impermeable surfaces, we're talking about asphalt, concrete, stone, brick, concrete pavers, these things that basically seal the surface. Whereas permeable surfaces are like natural planted beds, mulch beds, gravel, and permeable paving processes, turf, and then of course natural systems are permeable surfaces. So the impacts of these impermeable surfaces is the loss of mechanical and biological filtering of water. impacts also the pollution of surface water. This material is transferred into surface water bodies directly without the benefits of the filtration of a natural soil system. And also, flooding is magnified, and stream bank erosion hazard is exacerbated by this process, by increasing impermeable surfaces. And also, the water table is not adequately recharged. This water that falls as precip is not allowed to be filtered and recharge the groundwater system. Next slide, please. So the second to the last issue we're going to look at is biodiversity. And biodiversity is the variety of species and their habitats. And intact habitats play an important role in ecosystem functioning. And primarily we're talking about nutrient and water cycling, soil formation and retention, resistance against invasive species and pests. These plant pollination is an important part of a fully functional system, and climate regulation. You have a lot of hard surfaces. You have what's called urban heat islands that form. So climate's regulated by a highly biodiverse ecosystem. And then, of course, we talked about pollution and flood control. So, and basically, we're looking at about 17,000 plant and animal species that are threatened with extinction on the planet right now. And this is really a concern because 50 to 70,000 plant species that we use in traditional and modern medicine worldwide. We either use it to synthesize known medicines and treatments. So these plant species are very valuable. And of course, the soils provide the foundation for these habitats. Next slide, please. So the final issue that we're going to briefly talk about is farmland issues. In the U.S., we're losing approximately 1 acre of farmland per minute, and 25% of existing farmland worldwide is highly degraded due to poor management practices. And what we have to look forward to in the future is that farmers will have to produce 70% more food by 2050 to meet the needs of the world's projected 9 billion population. Next slide, please. So I guess in closing, I'd like to look at just a couple of references very quickly, just for your benefit. On the first page, we have number 1, Careers in Soil Science poster. This gives you a really good summary of the potential career in soil science. Next slide, please. And let's go one more slide down, please. And on this final page, if we go to the bottom, there's 2 additional references not cited. And in here is what's called soils education. And this link provides a variety of soils education resources for K through 12, different K through 12 levels. And there's a number of good resources and exercises within the soil education link for use in the classroom. And then the final is this soil judging manual that's put out by Purdue University. And this is a real good field guide to judging soils and their applications. And it's also used in soil judging competitions. So it's a very good reference that for the educator. That is pretty much winds it up for me. Are there any questions?
If you have a question, go ahead and raise your hand or type it into the chat. I see that Kay is suggesting a curriculum set called FBI Detectives on Decomposers, Fungus, Bacteria, Invertebrates.
Uh-huh. All right. Great.
Any other questions?
Lots of good resources out there.
So seeing and hearing none and knowing we're a little bit over today, Mark, I'd like to thank you very much for overcoming the technical difficulties. This has been recorded, and so the recording will be available if some of you didn't capture it all.